Welcome back. In this video, we're going to be talking about counting, which sounds really easy. It sounds like something children do. It actually turns out it's one of the more challenging aspects of this course. So let's dig in. All right, so we'll start with sets. So sets are collections of elements. So it can be often it'll be numbers, but it can also be anything. So for example, if we flip a coin, that set, which we could define as set C, would be heads and tails. So it contains two elements. Each have a 50% chance of happening, which we will eventually get to. So what we're doing now is we are defining sets so that eventually we can define probability. Which is specific elements of sets out of the total. We could also have a set of die roll possibilities. So we could define a set D to be the numbers 1 through 6 for every possible outcome of a die roll. So we can have numbers, we can have words, we can have letters. Sets can be anything, they are just collections of elements. So for our examples, let's define a couple of sets. So let's define set A to be the numbers 1, 2, 3, 4, and 5. And let's define set B to be the numbers 1, 3, 5, 7, and 9. So first, we'll look at a couple of operations. So first, we have intersection. So the intersection of A and B, we would write as A intersect B, so it looks kind of like an arch symbol. And that is going to be the elements that A and B have in common. So if we look at sets A and B, they share the number 1, they share the number 3, and they share the number 5. So intersection, we often will say, is like the word and. The things that are in set A and also in set B. So the answer there is 1, 3, and 5. If we look at a diagram of this, a Venn diagram of this, the intersection is literally where the two sets intersect. So that middle area right there, that is the intersection of our Venn diagram. All right, next we'll look at the union. So A union B, where the union symbol kind of looks like a U. So union is just all of the elements put together. So all of the elements in A put together with all of the elements in B. Doesn't matter whether they're in A or in B or in both. We're just going to list literally every element that is in either of those sets. So 1, 2, 3, 4, 5 from set A, 1, 3, 5, 7, 9 from set B. We just don't want to write anything twice. So we'll start off, let's write set A, 1, 2, 3, 4, 5. And then we'll write all of set B, but we'll skip over the things we've already listed. We've already listed 1, 3, and 5. So now we just need to list 7 and 9. And so that is the union of A and B. The union we often say is like the word or. So it is anything that's in A or anything that's in B. Now, in math, the word or is used differently than is used sometimes in everyday language. So, for example, if a mother told her child they could have either a cookie or a cupcake, what that mother probably means is that they could have one or the other, but not both. But in math, the word or does mean one or the other or both. So union encompasses all of those. So in our Venn diagram, union is going to be everything that's A and everything that's B, but also both. So everything in both sets, everything in all of those, all of that is the union. Okay, so those are our two operations, intersection and union. All right, the next thing we're going to define is a set U. So U is what we call the universal set. So the universal set is generally defined by the problem. I'm just going to make it up here But the universal set, we looked at two universal sets just a minute ago. So for a coin flip, heads and tails, that's the universal set. That's literally everything that could happen. Die roll, 1, 2, 3, 4, 5, 6. That's everything that could happen if you roll a die. So the universal set is what could happen. For example, if we were drawing a card from a deck, the universal set would have 52 elements, the ace of spades and the ace of clubs and the ace of diamonds. And so every single one of those 52 cards would be listed in our universal set. For this problem, I'm going to define it to be the numbers 1 through 10. So I'm just making this up. So for this problem, we just have a made-up universal set. But for a lot of problems, it's going to be defined by just whatever it is that we're looking at. So the universal set is the numbers 1 through 10. So we need that to be able to define a couple of other things, and those are called complements. So a complement are the elements that are not in A. So as a reminder, A contains the elements 1, 2, 3, 4, and 5. So a complement would be the elements not in A but are in the universal set. So that would be 6, 7, 8, 9, and 10. So if we were to draw the complement of set A, it would be everything would be shaded outside of set A. So the complement is we can kind of think of it as the opposite. It's not exactly the opposite, but it is all of the things outside of A. All right, set B, similarly, B complement. And A complement is written as A with an apostrophe. B complement is written as B with an apostrophe. So that symbol means complement. So B is the numbers 1, 3, 5, 7, and 9. So the odd numbers from 1 to 10. So B complement would therefore have to be the even numbers from 1 to 10. So 2, 4, 6, 8, and 10. So that would be B complement. Now, we can also find intersections and unions for complements. So we could find, for example, A complement intersect B complement. And so that would be the things they have in common. So both of them have the elements 6, 8, and 10. So none of those elements are either in set A or set B, so they are in the intersection of A complement and B complement. All right. Now, another notation that we will need is the number of. So typically, we're going to be dealing more with this notation than with what we've been writing, which is we write the elements of a set in these squiggly bracket lines. So we could write in of A, and that's going to be the number of elements in A, which is 5. The numbers 1, 2, 3, 4, and 5. So when we write numbers in this format, we're writing the number of elements, not which elements there are. So then we could write things like the number of elements in A complement intersect B complement, and that would be 3, because 6, 8, and 10, that's 3 elements. All right, let's look at a Venn diagram and let's label it. All right, so our Venn diagram here, we have set A represented by a circle, set B represented by a circle, and then we have a box around the outside with a U. So that U stands for the universal set. And then each little region we have labeled with R1 through R4. So these are what are called basic regions. So R1 are elements that are in A and only in A. R2, that's in the intersection, so that's elements that are in A that are also in B. And then R3, those are elements that are only in set B, not in set A. And then R4, those are elements that are neither in A nor in B. So when we label a Venn diagram, we're going to be writing the number of elements in each of these regions. So let's go ahead and do that. So in region 1, we'll go ahead in this case and also write what the elements are. So let's actually start with the intersection. So R2. So we looked at this earlier. Let's jump back to that real quick. The intersection of A and B were the numbers 1, 3, and 5. So there were 3 elements in R2. And those 3 elements, we could write those out. Those are 1, 3, and 5. All right. Now let's find R1. So those would be the elements that are in A that weren't listed in R2. So the elements that are in A and just A, not in B. So in region 2, that was 1, 3, and 5. So region A would therefore, or region R1, would therefore be 2. There are 2 elements in that region, and those 2 elements are 2 and 4. Both of those elements are in A, but not in B. Region 3, those are going to be elements that are in B that are not in A. So region 2 was 1, 3, and 5. So region 3 would therefore be 7 and 9, so 2 elements. We won't typically write out what these elements are. Typically, we'll just write the number of them in our Venn diagram, but for this example, we'll go ahead and write what they are as well. All right. So now we can find region 4, which would be whatever we have left over. So we have 2 elements in region 1, 3 in region 2, and 2 in region 3. So combined, those are 7 elements. They are the numbers 1, 2, 3, 4, 5, and 7 and 9. So the only elements missing there between 1 and 10 would be 6, 8, and 10. So there are 3 elements in region 4, and those 3 elements, 6, 8, and 10. All right. So now we have all of these listed. So notice here that region A, or set A rather, is the entire circle. And set A is made up of regions 1 and 2. So it's a common mistake to put the 5 elements in region A right there in region 1. But that's not actually it. We notice that region 1 and region 2, they add up to 5 elements, and those are the 5 elements in A. But the 5 doesn't actually go anywhere. It's just the sum of those 2 pieces. Some of the elements that are just in A and some of the elements that are in A and also in B. All right, so let's write a couple other things. Let's first write out the number of elements in A complement intersect B. So those would be elements that are not in A, but are in B. So that would be the number of elements that are not in A, but are in B. That's actually referring just to region 3. That's 2 elements. So what that says, number of elements not in A and also in B. So we're looking for elements that are in set B that are also not in set A. So that's 7 and 9, and that's 2 of them. All right. Let's do the number of elements in set A intersect B complement. So those would be elements in set A and not in set B. So those are going to be the 2 elements that are in region 1, the elements in set A that are not in set B. All right, so far so good, but this is where it's going to get a little bit challenging. All right, let's do the number of elements. Actually, one more before we get to the really challenging one. Let's do A complement intersect B complement. So those are the number of elements that are not in A and not in B, and that's region 4. That's the 3 elements that are not in A and also not in B. Okay. Now let's look at unions with complements. This is where it gets a little tricky. So the number of elements in A union B complement, for example. All right, so I want you to think about this one for a second. So pause the video here and see if you can figure out how many elements are either in A or are not in B. All right. If you got 5, that is a very common answer. The actual answer is 8. So if you got 8, great job. So the number of elements in A union B complement is 8. And I've got those 8 elements listed here. So A union B complement, that's anything that's in A together with anything that is not in B. So A, remember, was 1, 2, 3, 4, 5. B complement was 2, 4, 6, 8, and 10. And so the union, we just put those things together, everything that is in both of those sets together. So what we get is 1, 2, 3, 4, 5, 6, 8, and 10, 8 elements. So let's look at our Venn diagram to see what these are. All right, so those 8 elements are everything in A together with everything that is not in B. So what we end up with is regions 1, 2, and 4. So the part that typically confuses people here is, why is region 2 included? It's not in B. It says right there, not B. Well, the union is either of these two things. Either it's in A or it's not in B. If we exclude region 2, we're excluding part of A, but we don't want to do that. So A union B complement is everything in A and everything not in B. So when you're looking at a union, and this is really important, look at each piece separately. So first, look at everything in A. Then, separately, look at everything in B. Put those together, that's going to be A union B complement. Okay, so it includes everything in A and everything not in B. All right, let's try one more like that. Let's try the number in A complement, union B complement. All right, pause the video again and see if you can figure out the answer. All right, so A complement, union B complement. Common answer here is 3, which is actually A complement intersect B complement. That's the things not in A and also not in B. The answer here is actually 7. So we're including everything that's not in A, everything that's not in A, and everything that's not in B. So everything not in A, that's going to be regions 3 and 4. And then we're going to put that together with everything not in B. So everything not in B, that's going to be regions 1 and 4. So we put those two things together, and we get everything in region 1, 3, and 4, and that is 7. So again, with the union, we want to look at each piece separately. First, everything not in A, that's regions 3 and 4, and everything not in B, that's regions 1 and 4. So we put all of those together, and we get regions 1, 3, and 4. Okay. Now, one more thing we need to look at before we move on to a 3-set Venn diagram is the union rule. So the union rule is a formula that's going to come in handy. It is the number of elements in A union B equals the number of elements in A plus the number of elements in B minus the number of elements in A intersect B. And this actually makes sense. If we think about finding A union B, which is everything in A put together with everything in B, if we add all of the elements in A, so let's shade that. So that would be everything in A. And if we add that to everything in B, to try to get the union of A and B, what we've noticed is we've double counted region 2, the intersection. So that's why we subtract it out. Because if we just add A and B together, then we've double counted those in the middle. So we want to subtract those out once. Now, if we just know R1, R2, and R3, we can just add those 3 numbers together. But if what we know is all of set A and all of set B, we can add those together, but we need to subtract out the area we double counted. All right, let's move on to a 3-set Venn diagram. So a three-set Venn diagram, we have sets A, B, and C. So we have 8 regions here. So it gets quite a bit more complicated when we add a third set. All right, so we're told a lot of information here, but let's just start at the top and work our way down. Often on these problems, it actually helps to start at the bottom and work your way up. So try it either way, but anyway. All right. So what we're going to do is, as we go through these, we're going to label which region or regions each one of these refers to. So first we have number of elements in A intersect B is 13. Okay, so A intersect B, let's highlight that region. So that's A intersect B. That includes regions 2 and 5. So those two numbers together are going to add up to 13. But we have no idea how those are split up. Is it 1 and 12? Is it 5 and 8? Is it 3 and 10? We have no idea. But we do know it's regions 2 and 5. So A intersect B includes A intersect B only, not in C, but also A intersect B that is in C, because it doesn't say whether set C is included or not, so it includes both. All right, so we can't do anything with that piece of information yet, so let's move on to the next piece of information. It says the number of elements in A intersect B intersect C is 5. Okay, that refers just to region 5. So that is the intersection of all of those sets. It has to be in A, and it has to be in B, and it has to be in C. So since that's one specific region, we can go ahead and put a 5 there. Now, that tells us something about region 2, because we knew that this 13, A intersect B, that was regions 2 and 5. So if that's regions 2 and 5, regions 2 and 5 have to add up to 13, and region 5 is 5, that tells us region 2 has to be 8. So most of these numbers that are listed here aren't going to go on our Venn diagram, because most of them we're going to have to subtract to figure out what they are, because most of these refer to more than one region. All right, next let's do A intersect C. So A intersect C, that's going to be everything in A that is also in C, so that's regions 4 and 5, and we know that's 10. So if region 4 and 5 add up to 10, and region 5 is 5, that tells us region 4 also has to be 5. All right, next we have B intersect C is 5. So B intersect C, that's regions 5 and 6. So those two need to add up to 5. Well, region 5 is already 5, so that leaves us nothing, 0, in region 6. All right. Next, we've got number of elements in A intersect C complement. Okay, so that is elements that are in A that are not in C. So if we highlight the part of A that is not in C, so we just want all of set A that is not in C. So A is made up of 4 regions. Region 1, 2, 4, and 5. 4 and 5 are in C. 1 and 2 are not. So regions 1 and 2, they make up A intersect C complement. So regions 1 and 2 add up to 8, and region 2 is 8, so that tells us that region 1 has to be 6. So those can add up to 14. All right, B intersect C complement, so that's the part of B that is not in C. So B is regions 2, 3, 5, and 6. 2 and 3 are not in C, 5 and 6 are. So B intersect C complement is regions 2 and 3, and those add together to give us 15. So that tells us that region 3 has to be 7. All right, the next piece of information is that set C is 15. Set C is regions 4, 5, 6, and 7. So all of those have to add up to 15. Regions 4, 5, and 6, those add up to 10. So region C has to be 5. All right, the last piece of information is the number of elements in not in A, intersect not B, intersect not C. So that means it's not in the A circle, not in the B circle, not in the C circle. That is 3. Oh, and we missed, I started writing these regions out. Let's go back and write them out real quick before we finish. So A intersect C, that was regions, region 4 and region 5. B intersect C, that was region 5 and region 6. A intersect C complement, we said that was region 1 and 2. B intersect C complement, that was region 2 and region 3. And then C, that was region 4, region 5, region 6, and region 7. All of those were in set C. And then A complement, intersect B complement, intersect C complement, that was just region 8. So what you may have noticed, region 5 referred to a specific number, 5, and so did region 8. Every other number in this list of numbers was for multiple regions. So we have to figure out the ones that refer to a specific region first. We can start with those, and then we can build off of those because we have to subtract numbers out to figure out the basic regions. All right, that's it for today on counting. I'll see you next time.